That being said, I am going to keep, I'm not turning back on my please beep at me when a student comes in late to Zoom because I find it very disruptive. So, students on Zoom, tell your friends if you email me mid lecture, I can't get in the Zoom room, I'm lecturing and I don't look at my email. So, you have to like text a friend. If you don't have a friend, come see me in my office because that's a larger problem we have to solve first, right? And I can teach you how to talk to people and maybe, put forth a better, first impression to make friends. But I mean, we're scientists. Some scientists have a hard time making friends, right? So, yes, sir. I'm about to switch on. Thank you. I appreciate that, though. All right, let's talk about some chemistry. By the way, I was pleased, not bragging. I was pleased with myself that I was able to actually wing it without notes. I went back and looked at my notes. I'm like, oh, I covered stuff in like approximately the right order. So what I was talking about on Monday, and I believe today is Wednesday. And someone's unmuted, so please mute yourself. Okay, is you've got two molecules that are far from each other. Crap, why did I do that? All right. That are far from each other, and so we excite the donor with its excitation wavelength, and we get out fluorescence of the donor when the donor is by itself. When the acceptor is within molecular distance, you get a transfer of energy from the donor to the acceptor. It's not photonic emission. The donor does not emit fluorescence, which is not then absorbed, right? The absorption of the acceptor has to overlap spectrally with the donor fluorescence, but a photon is not exchanged, right? It's just that basically the energy from the donor resonates with the energy of the acceptor and then transfers via induction, essentially, right? And so now my acceptor will emit light. So if I was looking at this spectroscopically, right, and Fred is a really awesome technique. It's just super cool, right? If you look at wavelength and intensity of your fluorescence, right, and I'm just going to color them a little bit. Let's say I've got, I'm going to give you an example. A really common one. Green fluorescent protein. Called GFP. And yellow fluorescent protein. YFP. Whoa. I don't know what happened there. All right. If I was looking at the fluorescence, and I'm going to color code it, okay? Here's my green fluorescence, right? GFP. And this is what you get. You get GFP and no other fluorescence, okay? Let me just see if someone's here. Yeah, all right. Was someone texting you to tell you they couldn't get in? Oh, did you push the tile button? I love when that happens. It is embarrassing. I hope you feel bad, Jordan. Everyone look at Jordan and make him feel bad. All right. So you get fluorescence from the green fluorescent protein. Okay, so this is like sort of step one, right? In step two, GFP close to YFP, right? What happens, so this is like step one. In step two, the fluorescence from green fluorescent protein decreases, and then suddenly you get the appearance in step two of yellow fluorescence. The transfer of fluorescence from one molecule to the other is related to several things. One, overlap of spectra. So in other words, the absorbance of the acceptor has to overlap with the fluorescence of the donor. And that makes sense because the energies have to match up the transfer, right? This is quantum mechanics. So things are, they're quantized, right? I mean, if the acceptor is looking for energy that would correspond to, 550 nanometer light, that better be the kind of photon that the donor is going to emit, right? Okay, so that's one thing. Bless you, by the way. The overlap also, the alignment of the dipoles So the dipoles have to align in space. I was telling somebody, I think it was actually Jordan maybe on the way out of class on Monday, that ATP synthase is a protein that synthesizes ATP. You can figure that out by the name, right? And it's actually a rotor. It's a molecule that rotates on an axis. Taken Dr. Weber's classes. Dr. Weber is actually a world expert in ATP synthase. And there was actually a group that attached a fluorescent molecule on one side of the rotor and then on the other side of the rotor. And as the protein rotated to make ATP, the dipoles aligned and misaligned from the donor and the acceptor, and so the fluorescence transfer went up and down. And they were able to measure the rotational velocity of a protein in solution. Kind of cool, right? And then most importantly, the transfer is proportional to 1 over r to the 6th, which r is the intermolecular distance. That r to the 6th is super important, and it's going to come back to be a big deal for us when we talk about separations in this class. Most molecular interaction. Well, okay. Think about enzyme and substrate, right? Where does the substrate have to be relative to the enzyme's active site for the enzyme to do its work? Say it. Who said it? Yeah, right there, right? Thinking about it. At the active site, right? What if it's 50 nanometers away? Well, that's an infinite distance. Okay? I'm going to be gross again. I'm very sorry. Molecular interaction is no different than sexual intercourse. There's a defined distance where that happens. And larger than that distance, it doesn't. You're just looking at each other naked, right? Correct? I know. Dr. Pappas, why are we talking about sex in the morning? Because you're all asleep, damn it. I have to wake you up somehow. It's either sex or cocaine. It's the only thing that gets students engaged, right? I could talk about either one or both, because they sometimes go hand in hand. Molecular interaction, though, tends to have a 1 over r to the 6th dependence, whether it's fret transfer or binding or enzyme kinetics. If you move twice as far away as you were initially, your signal drops by 2 to the 6th, which is 1/64th of its original intensity, right? That's a huge drop off. Imagine if your grade, what if I took your final grade and divided it by 64 and then assigned your letter grade? Everyone would fail, right? My teaching evaluations would plummet. I'd be hated. It wouldn't really impact me whatsoever, by the way, job-wise. But, everyone would hate me, right? They'd be like, don't take his class because he just divides your answer by 64 and then gives you a score. Wouldn't that suck? What if you got 100? What's your new grade? It's an F, right? Isn't that terrible? All right. So the drop-off in molecular interaction is pretty much molecular proximity. Once it moves one molecule width away, nothing happens anymore, right? So this fret technique is very sensitive to the 6th power, sensitive, in fact, to how close the two molecules are. Why is that important? Because, I know some students online are like, Dr. Pappas, write something down on the board. I'm freaking out. All right, I'm going to write something down, right? 1 must be in molecular proximity. That's kind of cool, right? So we call this a spectroscopic ruler. 2, if fluorescent proteins are used, where do fluorescent proteins come from? So let me tell you what this, before I write this out. Where does a fluorescent protein, first and foremost, is what kind of molecule? It's made out of a lot of those, which makes it what? Or it's organic, it's a hydrocarbon. Think bigger. It's a protein, y'all. A fluorescent protein, first and foremost, is a protein, which is made of amino acids. Where do those amino acids come from? They're in a sequence, right? That causes them to fold into a tertiary structure. Where did that come from? Magic? Willpower? DNA, right? Don't remember how this works. Don't have to write out translation transcript. I can. I know it. Do I know why? Because I remember my biology. All right, you should too. Yeah, it comes from DNA. They're genetically encoded. So the beauty of using fluorescent proteins is I can attach the donor and acceptor to different genes. then tells me if those two genes work related to each other. Several Nobel Prizes have been given because of discoveries enabled by Forster resonance energy transfer, right? We now know that G protein coupled receptors work the way they do strictly because of fluorescence resonance energy transfer, because no other technique allows us to watch the interaction of working molecules in a living system. Think about NMR, think about all the other techniques we've learned about. You can't put a living thing, a living tissue or a zebrafish in an NMR. They don't like it, okay? You certainly can't get information out of it, but I can encode a gene. I can say, I wonder if radiation stress turns on heat shock proteins. And I can put a donor protein, fluorescent protein, on one of those genes and the acceptor on the other, irradiate my living biological thing, and look for threat to occur. And if it does, then I know that irradiating does cause that expression of that secondary protein. So the possibilities for threat are near limitless. Okay, so it's a really useful and cool technique. All right, we talked a little bit about the fact that fluorescence is linear with power, with your excitation power I0, is linear with concentration, with absorptivity, and with quantum yield, except when it isn't, right? But this isn't a Beer's law thing. I mentioned that it's not totally linear all the time. If you remember, I was talking a few days ago about absorbance. You've got absorbance of a molecule, right? And you've got fluorescence of that molecule, and there's this overlap region, right? And that overlap is a sort of spectroscopic cannibalism, if you will, right? Molecules emitting radiation, emitting light, can have some of that light absorbed by a nearby molecule of the same type. So fluorescein is one of the oldest fluorescent molecules ever. It's actually what makes yellow highlighters bright to look at, right? It's been around since, we've been using it since like 1900. It's one of the most common fluorophores. That fluorophore will absorb, in other words, a fluorescein molecule that emits light, a neighboring fluorescein molecule can absorb the same light from this overlap region. So because of that, if you remember the pre and post filter effects, you've got light coming in, right? Here's my light. And there's this pre-filter region where my light is being absorbed, my excitation power is being diminished by the sample itself, right? Then I've got a lens. Here's my observation region. And this region is the post-filter, right? That post-filter region is a part of, is a volume of solution that contains
Dr. Pappas, I can't hear your microphone.
Is he still frozen, or is it just me?
I think his microphone's not working.
No, it's his whole thing's not working because he logged out.
No, he's still in the room.
Well, okay. Now I have to admit everybody. Oh, everyone's back, maybe. Okay, can someone on Zoom unmute and say something so I know you can hear
It's
me?
working.
Holy crap. Sorry, that was really loud for us. All right. Thanks, everybody. All right. So anyway, let me get back to, I need to share my screen again, sorry. Wait, I'm the host. Did you see that? It said like I couldn't do it. I was like, you can't tell me what to do, Zoom. I'm the damn host of this. All right. Can someone very quietly on Zoom tell us if they can see the screen or on chat?
I can see it.
Thanks, Kendall. All right. Yeah. Hold on a minute. Watch this. Well, I can't turn down the speaker volume because then the in-class doesn't turn down. All right. Well, I'm more important lecture-wise than they are, so we'll go. All right. 2 answers is not good analytically. If you go back, think about the times we had to use the quadratic formula, right? Remember we had to do that sometimes? Remember the quadratic formula? It's a thing. And it gives you 2 answers, right? But it was always easy to discard one, like in analytical. Why is that? One's negative, right? You can't have a negative concentration, despite what my junior students sometimes write on their exams. Or when they write like 10 to the 50th molar, and I'm like, seriously? Like, this didn't even raise a red flag for you? In the past, I did have a student that got like a 10 to the 50th molar answer, and she wrote like, this is clearly impossible, I don't have time. And I gave that student full freaking credit on a 30-point question, because she understood it was wrong and would have corrected it with time is available, right? Like when I'm dying of a heart attack, I want someone to go, wait a minute, let me fix that, I messed up. Instead of just going, looks good, right? And leaves. So we don't want 2 answers, so this is a bad thing. So what do? Okay? Well, the beauty of this is if you're a good scientist, so how do you solve this problem, right? Because this is a problem. I know you're all thinking, I know this one, Dr. Pappas, we would dilute and remeasure. And you know what? That's not a wrong answer. So if you thought of that, I'm proud of you. We've learned something, okay? But what we would do is look at the spectrum. Has anyone ever encountered, like, yes?
So,
Jordan.
you say like, what you measure for whatever the chance would be. Okay, now you see when the concentration is high enough, what would be so approaching. Makes sense, like. Right,
So you've got 2 answers, one's higher and one's lower, so could you just say like the lower one's correct?
Well, I mean, so the essence of like, and doesn't that give us no information about the, yeah?
What it really tells me is that I'm no longer in a linear region.
Yeah.
So, which is useful, because then now you need to figure out how to solve that problem. Yeah. So how do you do this, right? You look at the spectrum itself. So here's an analogy. Have you ever encountered, like you're gonna make a sandwich and you encounter like moldy bread? So you choose not to use that bread, right? How do you know that it's moldy? Because it doesn't look right. Okay, good. So visual skill is the vital part of being a scientist, right? Stokes never would have discovered fluorescence if he hadn't looked at that bottle of quinine and gone, huh, that's weird, right? So here's my fluorescence. And I'm gonna normalize the data, right? So this is normalized fluorescence. What does normalized intensity mean, or when something's normalized? Relative, yes, and specifically what does it mean? Because it is relative. But when I say I've got normalized data, or I tell you to normalize your data because you work for me, and you're like, okay, and you go back to the lab and you're like, I don't know what that actually means, right? You just nodded to get out of my office. What does normalized data mean? Have you encountered this term before in science? You know what it is, Michaela? Okay, I hate to say this, but I have to ask the Zoom students to not participate over audio because for some freaky reason today, even your slightest whisper is deafening. I'm just gonna switch over. Does anyone on Zoom know the answer? No, you don't take the derivative, but I like that. I like your thinking. So I'll just tell y'all, normalized data is when you take all of your data and divide each data set by its maximum value so that all of your data goes from between 0 and 1. Does that ring a bell? All normalized data goes, that doesn't mean that they're equal in intensity. It just allows me to view them on the same scale, okay? So this is fluorescence. without self-absorption. And this is what it looks like, again, normalized. It's much more intense, but it's normalized. This is what it looks like with self-absorption. It's almost like the peak is missing, right? And so if you're plotting just that, that graph above us is just the plot of the peak. So naturally it's going to go up, it'll keep increasing until it plateaus and it starts to decrease. And then the wings of the fluorescence, the outlying part of the spectrum gets huge, the part that doesn't overlap with its own absorption and emission, right? So you're cutting out that area of overlap, which is where we actually measure the maximum, right? So how do you do this? You take the whole spectrum. If you take the whole spectrum, you will see the point where the peak no longer increases in intensity and then it starts to decrease and you're like, aha, now I need to dilute my sample, right? Too often we don't do this and people just move on, right? You can also just dilute it, but I would prefer to look at the spectrum. Because if you didn't, I would wonder what's really going on, right? There could be something else funky happening. Now, I don't know if you can tell, but I actually love fluorescence. Like, I think it's just the best. Like, chocolate. Chocolate makes everything better, right? If you don't like chocolate, something's wrong with you. Or like when you, like if you see a baby, everyone's like, that baby's cute. I mean, it might be a funky looking baby, but no one like hates a baby when you meet it, right? Babies are universally, we're hardwired to be like, that's an adorable thing that I should at least make a funny face at and move on, right? If you don't like babies, like in general, I mean, I'm not saying you want one, but if you don't look at a baby and go, that's cute, then something's wrong with you, right? It's like a sociopath test. Fluorescence is awesome. I feel the same way. Like, I love it more than some of my own biological children. Just kidding. Right? But there's one problem with fluorescence. It's a huge problem. We have this technique that is single molecule sensitive that can give us information about its environment if we want to, that can tell us if a molecule is interacting with another molecule. How cool is that, right? But there's one big problem with fluorescence, and that is most molecules don't undergo fluorescence. Now, you might wonder, some of you really like numbers in this class, right? You've come off of analytical, where it's all numbers, and now we're in this class that's super conceptual, and you're like, oh, this is like organic chemistry, but with less memorization, right? So, most molecules don't fluoresce. How many is most? I don't know. No one's ever done a catalog of it, but I would probably guess, just thinking about the known number of molecules that exist, that 99.9 something % of them do not undergo fluorescence, right? The number of molecules that undergo fluorescence that is measurable, that I can use analytically, is a very small subset of special molecules. And the number of things as an analytical chemist I may potentially be interested in is larger than that number. So what do you do? Add an extension, constituent, like a molecule, like maybe add a fluorescent molecule to it. Yeah, that's what I would do. And that's in fact what we do, right? So how do you solve this? Right, how to overcome this problem? You make it fluorescent. Because we're chemists. We have the power of the gods at our disposal. We truly do, right? That's why we're better than everybody else, scientifically speaking, right? Cormac, you ever tell this to your brother, like at the table, like, no, you're just a mechanical engineer. You just make stuff that doesn't fall over. I'm a chemist and chemical engineer. There are things that now exist because I created them, right? It's like creating children, but your chemicals don't just keep taking money from you, right? In fact, if you do it right, they give you money. All right, so how do you overcome? You make it fluorescent. How do you make a molecule fluorescent? There are two ways to do it, right? One is covalent linkage between your analyte, which is not fluorescent in this case, and a fluorescent molecule that we call a fluorophore, something that, sorry. something that brings fluorescent properties to it. And we just use chemistry. So I'm going to give you an example. If I want to label an amine, when would I, just thinking, how many of you are biochemists? A couple of you, right? Sadie? Yes. Sweet. All right, Sadie, I'm going to ask you, I'm going to put you on the spot. As a biochemist, are there amine groups that would be interesting to you? Can you give me an example of a molecule that has amine groups I would want to take advantage of? Thank you. Yeah, the amino acid, which makes proteins. Proteins seem like an important thing to study, right? In some level. I'm being facetious. Proteins are super important, right? Most of them don't fluoresce. Tryptophan and tyrosine will actually fluoresce on their own in the UV, but that's not really great. So I want to maybe make an amine fluorescent. I may want to attach it to a peptide or amino acid, right? Track it in a molecule, something like that. So it doesn't fluoresce. So what I use are what are called sulfonyl chlorides. And we're going to write down a reaction for once in this class, like real chemists. So if I have a fluorescent molecule, this is my fluorophore. Which one is it? Pick one. All right, it's attached to a sulfonyl chloride. It will react with a molecule that has an amine group on it, a primary amine. And you will get the fluorescent molecule linked So this is my analyte. Easy peasy. I didn't have a fluorescent molecule. I do some chemistry. I have a fluorescent analyte now. Except we have to take advantage. We have to do some tricks to this, right? We always add an excess, a molar excess, about 10-fold. Of the fluorophore. Sorry. Why would we add I'm looking at this reaction, so we add an excess of this, right? Why would we add a molar excess of one of the reagents? Is that louder, Aldo? You want to use all the fluorescents, you want to label everything, right? You want to label all of the analyte, correct? So why would I add, what principle do we use to add more reagent? Yes. It forces equilibrium towards the product side. It's a principle. Le Chatelier's principle. Thank you. One year I was teaching this class and I said that and someone raised their hand and they're like, what is Le Chatelier's principle? I'm like, who can tell me? And no one could. And they all had the same Gen Chem professor who ended up not getting tenure a few years before. And I'm like, duh, we made the right call, right? Nobody knew what it was. Le Chatelier's principle, right? If you add more reagent, the equilibrium drives to the product side. If you add product, the equilibrium drives in the reverse direction, correct? So we have to use the very same things that you forgot about in Gen Chem now to make things happen, right? Well, that's kind of an issue. What happens after the reaction? Well, I'm going to have, and I'm just going to make it a different color so you can see it clearly, excess. Excess unreacted fluorophore. But guess what? It fluoresces still, the same wavelength. My fluorescence instrument is not smart. It doesn't know that fluorescent molecule, whatever that FL with a circle on it is, that's my fluorescent molecule. It doesn't know if the fluorophore is freely floating around and unreacted, or if it has attached itself to a primary amine. So I must separate or remove excess dye before making my measurements. So we add a large excess of dye, label, you do a separation step. Now when we talk about doing separations like chromatography, this works really well because separation is built into the analysis, right? But you still have to do it. You can't just dump it in and run away. The second way is to use, and by the way, I should mention real quick, that fluorescent molecule is fluorophore of your choice. I have catalogs on my bookshelf in my office of thousands of reactive dyes. You have a wavelength you want to work at, we have a dye that you can buy that will match it, right? And we have the same dye could be in amide reactive form, in halide reactive form, in carboxylic acid reactive form. There's all these different functional groups that we can label based on, sulfhydryl groups, pick your favorite, right? It'll label it. And so that allows me to tailor. Now I not only can make a molecule that's not fluorescent, but I can also pick its wavelength and its other properties. Like I can pick a really bright dye or a dye that's less susceptible to photobleaching and things like that, right? Okay. The second way to make an analyte fluorescent is to label it with an antibody. Now, how many of you know what an antibody even is? Jordan?
Question.
Yeah.
For like the HCl.
Yeah.
So the heavy ions. How do you like that?
Does the chloride cause a problem?
Yeah.
Yeah. I mean, chloride. So whenever you add a large electron-rich anion, like a halide, it can quench fluorescence. It can increase the rate of external conversion. Going back to our clonidine discussion, right? Chloride is in every single sample at pretty high concentration, so adding a little more doesn't do it. It's really the bigger ones like bromide and iodide that really cause problems. Chloride's a light heavy ion, if that makes sense. So you're right. I mean, certainly if we had like a sulfonyl bromide, it would cause a lot of problems for us. But again, we just using glassware and touching things, at some point with a glove introduces a lot of chloride into your sample. It's everywhere. Good question though. So can anyone tell me what an antibody is first before we get into talking about fluorescence? What it does. Maverick? That's pretty good. I'm going to modify your answer just with one word. It's a protein, which is a molecule. Okay? Since people are getting vaccinated left and right, and in fact in Texas, they're just leaving needles on the ground you can step on and get vaccinated, right? They're everywhere, right? Sorry. So what's an antigen in general, right? Like a spike protein for coronavirus. What is an antigen, biologically speaking? But it's just a molecule that's not supposed to be there, right? It could be a piece of a membrane. It could be a protein on a virus surface, right? Like the coronavirus vaccine. It's a molecule that your body recognizes as belonging to potentially a foreign pathogen, right? See this molecule, an antigen. You have a helper T cell sitting around, floating in your bloodstream, and it goes, oh my God, and sees this antigen and grabs it. You know what? This drawing is starting to look a little bit like something my son would do as a middle school boy, so I'm just going to do that. Okay. Sorry. And then this antigen, helper T cell takes this antigen to a B cell, which then cranks out antibodies for the antigen. An antibody is essentially a giant Y-shaped protein with some sulfur bonds between it, right? And it has a binding site, there are actually two of them, on the ends of the Y, and this end here is a neutrophil receptor. Neutrophil. It's a pretty ingenious protein, actually. So it's a giant Y, right? That's its shape. It's a bidentate protein, and it can bind to two of the antigens. So if I inject you full of botulinum toxin, you will create antibodies for it, right? And if you don't die. And those antibodies will bind to that toxin. If suddenly I'm vaccinated now for COVID-19, and you come into my office and take off your mask and just sneeze everywhere and you're full of COVID, right? Kind of bag of COVID. I'm still going to be pissed. But hopefully, when all of that virus enters me, my body's like, we've been making antibodies for this thing, right? We're good. And I don't have to like fight off the response. This is how immunization works, which just like the flat earth, I now have to explain to people that you get vaccinated to prevent diseases and they don't cause autism. We were promised jetpacks and flying cars, my friends. This is what we have, right? You should be angry. So, the antibody has two functions in your body. One is just sticking a giant protein. It's like 150,000 Daltons, or atomic mass units, that we used to call them, right? That's a big protein. It attaches to the antigen. So if you're talking about a COVID-19 virus particle, it gets covered with antibody, making it difficult to do its job. It can no longer bind to and recognize and enter cell membranes, right? That's part of its job. And in the case of bacteria, the neutrophil receptor becomes a big deal, right? If you have a bacterial infection and you start pumping out antibodies to that bacteria, the neutrophils in your body, the most abundant white blood cell, go, wait a minute, I smell antibodies. And they go looking for it, and they will basically kill whatever that antibody is attached to, right? So it's like a homing beacon for your immune system. It's an ingenious concept, right? The important thing about antibodies, if they're good ones, specifically bind to one molecule only. From a fluorescence perspective, it's not that useful. So if I've got my analyte, make it a square, and I've got an antibody that's going to attach to it. So here's my antibody. Not that useful. But what if I do step one? What if I take my antibody and I derivatize it with a fluorescent molecule? So if I attach a fluorescent molecule to my antibody, now my antibody does the recognition aspect of it. So the fluorescent molecule that's attached to it does the actual fluorescence, and the antibody is the one that selects the wavelength. Every single one of you, from the moment you were born, they took a blood draw out of your heel. And a nurse went down to the blood lab and they took that blood sample and they attached fluorescent antibodies for the different blood types in your bloodstream, and they ran your very first white blood count and your very first leukocyte differential to make sure that your immune system works properly. When you go, how many of you have been to the doctor and they've taken a blood sample and they come back and go, well, your white count is up or whatever, right? We use fluorescent antibodies for it. It is a multi-billion-dollar industry. It's such a big industry, actually, that one of my students worked for Roche Diagnostics until recently, and they were buying antibodies for their work, and it was cheaper to buy an antibody-making company for $1 billion and say, we are now your only customer, than to continue buying antibodies from them. We are in the wrong business, ladies and gentlemen, right? I need to start my own antibody factory in Lubbock and just roll around in gold coins all day like Scrooge McDuck, right? You don't even get that reference, probably. You might, Misty. But the rest of you are all babies. Misty's a baby as well, but slightly not as babyish baby. All right. Why is this important? If I can make an antibody for my analyte, I can label it specifically. I can just throw the antibody into a very complex sample like blood, and it's going to find my analyte and bind to it, right? Really great. There are two kinds of antibodies that are used. I'm not going to talk about them. They're polyclonal and monoclonal. Polyclonal antibodies are when you take an antigen and you inject it into a living animal like a mouse or a horse. Let it make antibodies just like we do. And then you take some blood out of the horse, or if it's a mouse, all of the blood. And then filter out and purify the antibody that you need. A monoclonal antibody is actually where we do some pretty Frankenstein stuff. We take a cancer cell, which is immortal, and a plasma B cell, which makes antibodies, and we fuse them into one cell called the hybridoma that has the antibody-producing capabilities and immortality. And that cell creates the same antibody day in, day out. And that's where the big money is. You can make a monoclonal antibody. That's actually, anytime you see a drug, by the way, that ends with MAB, stands for monoclonal antibody. So you may see, like in your, magazine you're reading, well, like if it's a magazine with news in it anyway, you'll see drugs for cancer that all end with MAB. They'll have like an unpronounceable jumble of letters that all end with MAB. Those are monoclonal antibodies for cancer cells. Okay, it's a huge business. So that's how we make molecules fluorescent and do all our fun stuff. But now let's leave fluorescence behind entirely, right? We've talked about fluorescence, we've mastered it, we all feel good about it. Let's talk about vibrational spectroscopy. You've all done this before, right? You've done infrared spectroscopy, for example. There are two, infrared and Raman spectroscopy. You may have learned a little bit about Raman spectroscopy, and I'm going to tell you now ahead of time, this will be the most confusing part of my already confusing course. Like, I literally see students' brains melt during the lectures in the next few days, because we'll be talking about things that don't exist, but yet we observe them and things like that. It'll be great. But when y'all did vibrational spectroscopy, you probably first encountered it in organic chemistry, right? And what do you use it for? Functional groups, right? Like, oh, I have a carboxylic acid, right? Like, you made a molecule in organic and you probably did IR, right? And said, oh, there's an amine there, right? I did the right thing. That's part of it, right? It's a qualitative measurement. And why can we do that, right? We get functional group information because different bonds vibrate at different frequencies, right? A CO double bond vibrates differently than a CO single bond. And those are different than a carbon-carbon double bond, right? And so we have different vibrational modes. And there are all kinds, but there are things like, I'm just going to draw like an atomic molecule, like a symmetric stretch, right? Those of you on Zoom at home are missing this awesome pantomime, but it's like two bonds elongate the same direction, right? An asymmetric stretch, they don't. So there's all kinds of weird stretches that you can think about, right? There's rocking of a plane, so in other words, the bond lengths don't change, but the bond angle does, okay? There's out of plane wagging. Benzene rings and aryl rings breathe symmetrically or asymmetrically. We call that ring breathing. And you would appreciate that probably certain bonds vibrate faster or slower, right? How many of you have taken PChem2 or are in it now? Do y'all like PChem2? This is my favorite class. I know, right? I got to it, and I hated PChem2 until we got to harmonic oscillators. And for some reason, I understood them, and I'm like, oh, I'm not an idiot, right? Like, there's an aspect of PChem I understand. Yes, Jordan.
Oh, yeah, good question.
I'm not going to say anything. Let's end that discussion now. I'm not criticizing you for saying that, but let's not discuss the qualities of my colleagues, good or bad, in this classroom, please. I had a great professor. He was actually pretty awesome. He worked on the Manhattan Project as like a high school intern. He was so old, and he was like old school 50s, horn rimmed glasses. He looked like, you know, he was like 92 when I took his class, and just like ran into class every day, like super energetic. And I'm like, that's when I decided that I was going to become a chemist, because all my professors were really old, but like with it, like mentally sharp and in good physical condition because of all of the benzene vapor, right? Like, you're partially preserved from all the aldehydes and things you've been breathing in that building, right? And I'm like, man, every chemist I know has lived a long, productive, happy life. They're all in their 90s and like playing tennis. This is clearly a career. If you don't like die in a horrific lab accident early, you make it past your 40s, you're going to live a long and pretty awesome life. I actually thought this. Thank you, Dr. Wellner. Okay, he was great. But it's a harmonic oscillator, right? And so harmonic oscillators, like two masses on a spring, right? The spring tension partially determines the vibration of that spring, correct? And what else plays a role? If you have two objects like A and B, two masses, right, and a spring, I promise I will not write a Hamiltonian, right? There's tension, which helps determine the spring oscillation frequency. But what else plays a role? The masses, right? Absolutely. And so hydrogen, turns out, it's a pretty simple molecule, molecular hydrogen, right? It's got one bond, and it's the most energetic bond of all. It's the smallest mass, it's the highest frequency of oscillation, about 4,000 wave numbers, right? So we can use vibrational modes to get functional groups, and we can put on our Sherlock Holmes hats and put together a molecule. If any of you go to grad school for chemistry or biochemistry, and I highly recommend that you do, because it's a great career, I get paid to do this, you guys. Like, every morning I wake up and I'm like, I can't believe tech pays me to come and do this. it's an awesome career, right? Think about it. If you don't know what you want to do, I highly recommend. Also, you get paid to go to grad school, and you get free tuition. No debt, friends. So if you can eat pizza for 4 or 5 years, and you like working in a lab, get your doctorate. It's totally worth it, right? So anyway, sorry. If you take a graduate course, if you go to grad school, there's a graduate course called molecular spectroscopy or organic spectroscopy, where you take IR spectra and NMR spectra and mass spectra, and you piece together the molecule that you made or were given, because that's what we do. How do we know the structures of these molecules? Because of things like infrared, right? So we get vibrational information. We use FTIR, which I've already covered, to get spectra, right? To obtain spectra. Now you've all learned FTIR, so I'm not going to delve into it. Like we already talked about Fourier transforms and the instrumentation of it, and you've all used FTIR in person to collect structural data, right? So I'm not going to cover that actually, for a pretty good reason, and that is you can do it, right? I am going to on Friday talk about one of my favorite molecules, which is cocaine. We're going to look at its IR spectrum and kind of dissect it, right? I may get a little political because sentencing laws for cocaine are inherently racist and classist, right? But we'll also talk about the inherent problem with FTIR, and that is, how many of you have ever measured an aqueous sample with FTIR? None of you. You want to know why? Because water absorbs the IR like nobody's business. Its absorptivity is the largest of any molecule, right? So we have to work with non-aqueous samples. So for years, people walked around going, if only we could get vibrational data in water, because everything exciting happens in water. You're only here because of water-based chemistry, right? I know. Totally gross today, I appreciate it. We're going to talk about Raman spectroscopy because that is actually how we get vibrational information from aqueous solutions, which is kind of a game changer, all right? So come to class on Friday, we'll learn things, you'll be entertained. Thanks, Zoom fam.